Thank you. So, hi everyone. So it's a truth universally acknowledged that coding interviews are uncomfortable. You're on the spot, you're on your own, and you're trying to think under immense amounts of pressure whilst trying to show your absolute best self. If you're lucky, you'll have an encouraging interviewer. If not, well, it's just not that nice of an experience. So what I'm going to do in this next half hour is try and make the experience a little less daunting by giving you a heads up on what you need to know to be able to keep your cool and equip you with the foundational know-how to solve problems from first principles if necessary, making sure you're ready for anything. So my name is Claire Byrne, and I'm a data engineer at Rapid7 in Belfast, Northern Ireland. I've been volunteering with Women Who Code for around 6 years now, and at this stage, I've done a few coding interviews in my time. So one of the most unexpected things that I've learned over the course of many, many interviews is that technical interviews are a skill. They're not an innate talent. They can be learned and improved, believe it or not. So let's launch right in. Everyone loves data structures, right? I know the phrase sends a chill up a lot of people's spines, but personally, I'm actually in love with the concept of data structures. Just as a blacksmith's tools are their hammers, and a painter's tools are their brushes, the tools of a software engineer are data structures, and the algorithms that can be built from them. You don't need to be able to recite the code for these data structures on the screen off by heart, but you need to have an idea of what they are and how they're used. So to continue with the analogy, if a painter has no knowledge of how, say, a palette knife works, they're going to have to use a brush for oil paints and end up with a less desirable result than they could have achieved. So what I'm trying to say in a really roundabout way is you can't use your most effective tool if you don't know it exists. So awareness of the advantages and disadvantages of these structures is key. Each structure comes with its own disadvantages and advantages. It performs a different task and meets a different goal. And it's important to have all these tools in your belt when you're asked to tackle a problem of the software engineering trade. So I know this looks like a lot, and there are many more, but it's actually not that bad, honestly. A lot of data structures are subsets of a few main ones. So if you take a step back, you can see that stacks and queues can be implemented using linked lists. And similarly, heaps and tries are just a subset of trees, and trees are a subset of graphs. They're a form of acyclic undirected graph if you want to get specific and scary. And arrays, which are sometimes known as vectors, are one of the ways in which we can build hash maps or associative arrays. So I'm just going to take you through these slowly. So let's explore these structures in more detail then. Linked lists are an ordered collection of objects, but they differ in structure from normal lists and arrays in that they don't have to be stored in contiguous memory space, and they don't have to contain data of the same type in each node. Linked lists are not index-based. They store references to the next element of the list as part of each node. So you can see here on the slides, there's a data part and a pointer part. So a linked list is just a collection of these nodes of data and pointers. The beginning node in the list is called the head, and the last node in the list is usually distinguished by the fact that it will point to none or null. Other data structures such as queues, stacks, and even graphs in some languages are all implementations of linked lists. They can also be useful for caches and lifecycle management within the operating system, and for traversing trees and all that sort of thing. Linked lists are really useful. So queues and stacks, as I said, are simply, or can be simply, implementations of linked lists. And they simply change the way the data is accessed within the structure. So a queue is a first in, first out data structure in general, meaning that data is inserted at the beginning and taken off from the end. So if you think of a queue in real life, if you're queuing for a restaurant, the people who get there first will be the first to get in. So if you just think of that as a real life example, it's pretty easy. Queues always have a pointer to the beginning and the end of the queue as well. So on to stacks then. Stacks are last in, first out data structures, where the last thing to be put on top of the stack is the first thing to be taken out or popped. So again, think of stacking objects in real life. You can't take something from the bottom of the stack, or it'll fall over. Stacks always have a pointer to the top element, which in turn points to the next one down and the next one down. So as I said, these structures can be implemented without, well, these structures can also be implemented without using a linked list as the base, but I always find it very helpful to remember that they're essentially subsets of linked lists. So on to trees then. Everyone loves trees, right? Yeah, we're really branching out with this data structure. Okay, that was a terrible joke. Within computer science, trees are well known as a non-linear data structure, and they're used for everything. File system, it's a tree. Call graph of a program, it's a tree. They don't store data in a linear way like stacks, vectors, or linked lists. They organize data hierarchically. So as with other data structures, a tree is made up of nodes of data connected by pointers called edges. I love tree data structures because they use a ton of actual tree analogies that make a lot of sense. So for example, the last nodes in the tree that don't have any other child nodes are known as leaves. And a tree always has a starting node classified as the root node at the very top of the hierarchy. I'm all about those analogies. So the most basic thing you need to know about trees is that each node in a tree stores pointers to its child nodes. So there's many, many different types of trees, and many different ways of getting data out of trees called traversals. Basically, if you know how to traverse a tree and which type of tree is appropriate for the task at hand, I'd say you could solve almost any problem. Plant a tree, solve a problem. So I'm going to take you through the types of traversal of a structure called a binary search tree. So this is probably one of the most important types of tree that you'll come across. And many other types of tree stem from this one structure. Oh, that was another tree pun, by the way. A binary search tree, or ordered binary tree as it's sometimes called, is a type of binary tree where the nodes are arranged in order. So for each node, as you can see in slides, all elements in its left subtree are less than or equal to the root node, and all elements in its right subtree are greater than the root node. So you can see that that holds true for the subtrees as well. So 1 is the least, and it's on the very left, and 7 is the greatest, so it's on the very, very right. So there's many types of traversals, as I've said. So in-order traversal is very commonly used on binary search trees because it returns values from the underlying set in order. So if you just go through this with me, I guess, if you go to the left subtree, and you go to the left subtree, and then you go to the left node of that subtree, you get 1. And then if you go to the root of that, you get 2. And then if you go to the right node of the left subtree, you get 3. And then following that pattern again, you go to the root, which is 4. And then you do the same for the right subtree. So that's 5, 6, and 7 again. So pre-order traversal then, that can be very useful for duplicating a tree itself. So this is a common traversal used in compiler design and embedded system design, as it's very space efficient. And then post-order traversal, I'm not going to go through all these in detail because you can sort of see how it works. But it's very useful when you're deleting or freeing nodes from memory. So if you're working in a very memory restricted environment, it's a good algorithm to have under your belt. So depth first search can be implemented very easily using a stack, and breadth first search, which is basically where you traverse a tree by level rather than depth, can be implemented using a queue. So here we're seeing that these are very useful already. All data structures are very intertwined nicely. So I encourage you to look up different uses of different types of traversals for different trees. Using a particular type of traversal can give you different views on a dataset for free, which is why trees are such a versatile and elegant data structure, in my opinion. I'm a bit of a tree hugger, but let me show you what I mean by an elegant data structure using a different type of tree. So this is a heap. A heap is a complete binary tree-based data structure with specific ordering properties. So the ordering can be one of two types, as you can see here. A max heap, where the value of each node is less than or equal to the value of its parent. So this means that the greatest value will be at the root node. And also, again, the same property must be true for all subtrees. And then you have a min heap, which is the exact opposite. So where the value of each node is greater than or equal to the value of its parent. So the smallest value is at the root. So heaps are used whenever the highest or lowest order element needs to be removed. So because of this, one use of a heap is to implement a priority queue. So every time the greatest or least element is taken from a heap, and it's reshuffled to give the greatest element or least element, whichever type of heap you're using. So I'm not going to go into the actual implementation details here because of time, but be sure to look it up, and I've got some excellent references at the end that you can use. So the next data structure we're going to cover is Hashmaps, or sometimes called dictionaries, or sometimes called associative arrays. These are all the same thing, and I can guarantee you've used these in a programming language without realizing. They're essentially data structures that allow key value mappings, and they come as built-in structures in most languages, including Python, Ruby, and JavaScript. So how do they differ from normal arrays? And why are they so much better? We can think of a hash map like a set of drawers, and each drawer has a label. So, for example, if we want to access a book in these drawers, we don't have to go through all the drawers of other stuff to find this book. We simply open the drawer labeled books and search there. So this basically translates to, if I want to access the value of a certain key, I can just go straight to that key in the hash map. If I was using an array instead of a hash map to hold all my values, I'd have to go through every index of that array until I find the value I'm looking for. So you can pretty much think of hash maps like a bit of a hack on top of arrays, using a hashing function. They just allow us to use flexible keys instead of being stuck with like sequential integers as indices. They're a bit more fun than arrays. Okay, so there's a lot more to data structures than that. But in the interest of time, let's launch right into one of the most important concepts you're ever going to need to know for a tech interview. Big O notation. Ooh. Okay, that was an attempt at a bad Big O joke. It's probably a good thing I can't see you not laughing at me. So just what is Big O notation then? Oh, cool. I'm getting a lot of reactions in the chat. Thank you. Maybe I should change career. So Big O notation is used in computer science to describe the performance or complexity of an algorithm. So it's highly likely that within at least one part of your tech interview, that you'll be asked some questions on algorithms. So specifically how to solve a problem and then improve and iterate on your solution. It's really important to be able to talk about code in relation to its time complexity, because everyone wants fast code, right? And I found that learning about Big O has improved my algorithmic thinking in a really big way. So Big O also specifically describes the worst case scenario of an algorithm, and it can be used to describe the execution time required or the memory space used by an algorithm. So there are other more theoretical and mathematical ways of describing the best case and the tightly bound best and worst cases. But honestly, unless you're pursuing a PhD in this topic, the only one that's ever used in industry is Big O. So I'll break this down for you then. So constant time, or Big O1, This describes an algorithm that will always execute in the same time or space, regardless of the size of the input dataset. So a silly real-world example of this would be if you want to send a file via airplane to a friend. The size of the file really doesn't matter because there's other bottlenecks here. So no matter how big this file gets, the time will stay the same, unless you have a file that's like bigger than an airplane. Another more grounded example would be this code snippet here. Hopefully you can all see that. So in this snippet, the size of the array will not affect the time this function takes to run, as it's just checking the first element of the array. And that's never going to move or get bigger or anything. It's just always going to be the first value of the array. So it's unaffected by the size. Hopefully that makes sense. So now we'll move on to linear time. So this bit of code is a simple example that denotes searching through a list for a specific string. For each element in the list, it compares this element to the desired element, and then returns if the element is equal to the desired element. However, the problem is we don't know where this element will be in the list, and it could potentially be at the very end of the list, which, if the list is long, will take more time. So how do we denote this in big O notation then? The time will grow linearly with the size of the list, because we don't know how long the list is, and we don't know where the element is. So with the size of the list being n, the time complexity will be big O n. This example also demonstrates how big O favors the worst case performance scenario. A matching string could be found during any iteration of the for loop, and the function would return early. But as I said, big O notation will always assume the upper limit, where the algorithm will perform the maximum number of iterations. So now we're getting into scary territory. So this example here will go through an array, and for every element, it will go over every other element in the array and print out the element in focus alongside the other elements in the array. So I'll help you visualize this. You can visualize it if you write it out simply with an array containing the numbers 1, 2, and 3, and then pair each number with the other numbers in the array. But I'll not just tell you to do this, I'll do this myself. There you go. So I'll give you a quick example here, because it can be quite hard to visualize. So for each of these numbers in this array, we're going to pair it with each of the other numbers in the array, starting with the first number. This is going to result in a sort of square matrix, which means that the runtime will be exactly what it looks like, a sort of square, which is the square. Who would have thought it? This is also true for the space complexity of this piece of code, although in interviews I found that time complexity is generally more of a pressing issue than space complexity. Still useful to know though. And a useful rule is that if you see a nested loop, each using one array, it's generally a time complexity of big O n squared. Okay, getting even more complex again. So big O 2 to the power of n denotes, it's exponential. It denotes an algorithm whose growth doubles with each addition to the input dataset. So honestly, you're probably not going to see this very often unless you have a really inefficient algorithm. So an example here will give you the recursive calculation of Fibonacci numbers. It doesn't matter if you don't know what Fibonacci numbers are. The thing you need to take away from this snippet here is that this is a recursive function, and each function call will call itself twice. So let me visualize that for you again, because I'm a big fan of visualizations. I don't have a mathematical brain in my head, so yeah, you need to draw it for me. Okay, so again, hopefully you can see this. A lot of people will see two calls to each function on each level and think automatically, oh, this must be big O n squared. So this isn't quite right, and I'll try to show you why. So each recursive iteration calls itself twice, as I said, and this is a very important pattern to remember. So Often when faced with a recursive function, the runtime will be the number of times each recursive call branches to the power of the dataset length. So if you can't work it out on the fly, just use this kind of formula here. So here's a nicer one. Onto big O log n. So logarithms they're mystifying. They're black magic. I don't know. But this can be a bit of a tricky one to explain. But essentially, if it's the opposite of exponential, it's probably big O log n. So the best way to identify this in an algorithm is to think of all the algorithms where the problem space on each iteration is reduced by half. So I'll illustrate it with another example. You've hopefully all heard of binary search. It's a technique to search sorted data sets. So this works by selecting the middle element of the data set, essentially the median element, and comparing it against a target value. If the value matches, it will return success. If the target value is higher than the value of the search element, it will take the upper half of the data set and do the same thing. Otherwise, if the target value is lower than the value of the searched element, it will perform the operation against the lower half of the array. And it will continue to halve the dataset with each iteration until the value has been found, or it can no longer split the dataset. So you can see here with this example, if we're searching for the number 9, we would take the middle element, which is 5. I'm not sure how it works. Well, it'll either take the upper or lower if it doesn't have an actual middle element. So we'll take 5 and compare it to 9. So 9 is greater than 5, so it'll take the upper half of the array. So then it'll search the median again, which is 14. So 9 is less than 14, so it'll take the lower half. And then it'll find the element it's looking for. So basically, the iterative halving of these data sets produces a growth curve that kind of peaks at the beginning and slowly flattens out as the size of the data set decreases by half each time. So just for an example, an input data set containing 10 items will take 1 second to complete for argument's sake. A data set containing 100 items might take 2 seconds, and a data set containing 1,000 items might take 3 seconds. Doubling the size of the input data set has little effect on the growth, as after a single iteration of the algorithm, the data set will be halved and is therefore on a par with the input data set that's half the size. Hopefully that makes a little bit of sense. So this basically tells you how efficient all the big O's are. And I find it quite helpful to just remember the colors. Yeah, take a screenshot if you like. So now that I've completely overloaded you with information, I'll leave you with a few awesome links that I used to build this presentation and that I've used for study in the past. You don't need to be a super duper expert to be able to pass your coding interview, but a solid foundation in data structures in your mental toolbox can work absolute wonders for your confidence during a tech screen. And remember to talk through your thought process during your interview, because that's what interviewers are interested in. And treat the interviewer as more of a colleague and not an enemy. You don't have to be scared of your interviewer. They're usually there to help and see how you think. And a good interviewer should be collaborative and helpful when you're stuck. So the book at the top of these references is essentially the golden rule book when it comes to tech interviews. And it helped me to understand big O notation better than I ever did in university. Also the Medium resources by Mariam Jaludi and sorry, I don't know how to say that. Base CS on Medium is fantastic, as are all the comics by Julia Evans. So consider going to these links. I have so much respect for all of these authors. And the last two are GitHub resources that have exercises and tips for coding interviews. So with that, I'll say thank you so much for listening, and feel free to contact me at any point on any of these socials. So my name is Claire Byrne, and I'm a global ambassador for Women Who Code and a software engineer as well. So thank you so much for listening. It's me.
Awesome. Thank you so much, Claire. What a funny and insightful talk that you had. We have a few minutes for questions that have come through. If you'd like to answer any. Folks are asking, will you be sharing the slides for
yes.
them to use?
I can. I don't know where to share it exactly.
Maybe if they reach out to you via email, you can potentially share with them. So folks on the line, if you want to connect with her. And this video will be uploaded to the Women Who Code YouTube channel. And so you'll be able to go back through this amazing content. And then I think I saw someone asked if you reviewed the Bigos notation of n factorial, maybe potentially.
I didn't. Sorry.
There.
Yeah, that's one I missed out. Sorry.
No problem. I'm trying to see if I see any more questions in the chat. Anyone else have anything? There seems to be a big trend towards conducting technical rounds online without an interviewer. What's your insight on this hiring trend? That is the new one.
I think it's important to have like a face-to-face conversation with an interviewer, but I do quite like technical interviews or like coding challenges where you're just kind of left to it. I think it's a little less daunting because you can just think on your own and you don't have someone like watching you the whole time. So I do quite like that, yeah.
There's another one. If you have a technical interview and get asked to evaluate the complexity of a piece of code, do you have any tips on how to answer it calmly? I tend to just go blank.
Well, just talk through your thought process, really. And like your interviewer will probably ask you, or they'll probably like be okay with it if you bounce ideas off them. So if you kind of like talk through, right, I've got this array here, and the complexity here would be like big O n if this was a case. So yeah, just bounce ideas off your interviewer and breathe.
Great tips. Someone asked, what's your favorite data structure, or what do you find yourself using the most often in industry?
My favorite data structure is a tree. More specifically, a prefix tree. I really like those because they're very like space and memory efficient. And like if you implement them right, they're pretty elegant. But honestly, in industry, I find myself using Hashmaps most, or dictionaries in Python. They're just so useful. I'm gonna share my slides here as well. I think I can just get a link here.
Perfect.
So give me 1 second. Okay, I'll share it in the chat here.
So she will be posting the link to her slides in the chat. Thank you so much for your time, Claire. This was a fantastic conversation. Again, folks, feel free to reach out to her with the contact points that she's listed on these slides, and enjoy the remaining sessions that you all have. Thank you so much.
Thank you so much for moderating, Brianna.
Of course. Have a good one.
Bye.